Okay, sorry about that noise. All right, so here we go. We want to. So basically, what this question is kind of asking two things. Um, One, if we have a Fourier transform of a function, can we in principle recover f? In other words, um, given a function, given a Fourier transform of a function, are there multiple functions who have that as a Fourier transform? So we've got f hat here. We know that the Fourier transform of f is going to be f hat. And we want to ask the question, could there be another function whose Fourier transform is also f hat? And the answer is basically that there's only going to be one function. For every Fourier transform, there's going to be one function. There's going to be one function who has that as a Fourier transform. Now, that's not exactly correct. If you want to know more about why it's not exactly correct, that's fine. But in principle, there's just going to be one. And we can make that statement precise about there only being one. Okay, but now what we want to do is we want to know practically, is there a way? So now that we know that there's only one, is there a way to compute the inverse Fourier transform? In other words, is there a practical formula, given a Fourier transform, is there a practical formula to find the function given its Fourier transform? And the answer is yes. It's a very good formula. It's going to look very much like the Fourier transform itself. And my claim, I'm going to write this as my claim. If f and f hat are both continuous, I'm not going to write, well, if f and f hat are continuous, continuous and integrable, then f of x is going to be equal to 1 over 2 pi times the integral minus infinity to positive infinity. We're integrating f hat, and the integration is going to be in the c variable, EICX dc. Okay, so notice the difference here between the Fourier transform. First of all, here we have the 1 over 2 pi. We didn't have that in the Fourier transform. We're integrating with respect to c instead of x, so we're going to get out a function of x. And in the exponent, we don't have a minus sign. We have a positive sign. Okay, and I'm basically just going to explain why this is true. We're just going to do a computation. By the way, I think maybe a little bit later on when we look at separation of variables, we'll have a better idea where this formula comes from. You can also look in the later sections in chapter 6. It'll give a better idea of where this formula comes from. It's not just an educated guess. Okay, so let's explain why this is true. So I'm going to compute 1 over 2 pi. Okay, I'm going to compute 1 over 2 pi. I'm just going to compute what this is. We're going to have minus infinity to positive infinity. Okay, so what is f hat? F hat is the integral minus infinity to positive infinity, f of z, e to the minus I c z dz, e to the I cx dc. All I'm doing is this right here is just equal to this in the brackets. Okay, so now this is equal, whoops. I'm giving myself some room here for a reason. So this is equal to 1 over 2 pi. Actually, I don't need to give myself room yet. Sorry. This is equal to 1 over 2 pi times the integral minus infinity to positive infinity. Actually, I do need to give myself room. Sorry. You'll see why in a minute. I know it seems ridiculous now. It's basically because I don't want to rewrite a whole bunch of stuff. So this is equal to 1 over 2 pi times the integral minus infinity to positive infinity. Basically, I'm just getting rid of the brackets. Minus infinity to positive infinity. I'm going to have f of z. Now I'm going to combine the exponentials into 1, so it's going to be I, c, and we're going to have x minus z. dz is the outer integral, and then we're going to have the c in the inside. Okay, now what I want to do now, I want to swap the order of integration. But we're not going to be able to. It's not going to be. We're going to do an illegal swap of integration, and I'm going to explain why, and then explain how to make it right. So I'm going to swap the order of integration. This is going to be minus infinity to positive infinity. So now z is going to be on the outside. So you might remember the Fubini-Tonelli theorem, or I forget exactly what it's called in Calc 3, where you're allowed to interchange the order of integration. Like if you're integrating a continuous function on a closed set, on a compact set, you're allowed to swap the order of integration. So I want to swap the order of integration here, but the problem is we're integrating not over a compact set. We're not integrating over a bounded set. We're integrating over all of the real line. So that's why there's going to be a problem. But at any rate, z is now going to be the outside integral. So I'm going to have f of z here. And on the outside integral is going to be dz. And now the inside integral is going to be the integral from minus infinity to positive infinity, e to the minus I c x minus z dx. Okay, but now notice what's happening here. This inside integral doesn't decay any, and it's going from minus infinity to positive infinity. Compute what this integral is, and you're going to see that it does, like, write this in terms of sines and cosines to really see what's going on here. You're not going to get an integral that exists. You're going to get something like the limit as r goes to infinity of cosine of r plus I sine of r, or something along those lines. And that limit doesn't exist as r goes to infinity. It just doesn't exist. So this inner integral does not exist. Okay, so if we change the order of integration like this, we're doing something illegal. And it's not even that it's illegal. I mean, that is a problem, but we can't really even make sense of it right now because, you know, the thing in brackets doesn't exist. Like, it doesn't have a well-defined thing within our framework. So we're going to have to do something a little bit different. And basically, to do something a little bit different, we're going to go back, and when we do the improper integral in the step above, we're going to be a little more careful here. This is equal to the limit as r goes to infinity, and this integral is going to be from minus r to r. Okay, so now because we know that the outer integral is over a bounded set and the inner integral f is a continuous, is absolutely integrable, we can now do a legal change of integration. So this is going to be the limit as r goes to infinity, 1 over 2 pi. We're going to have minus infinity to positive infinity on the outside. We're going to have f of z, dz on the outside, and the integral is going to be, the inner integral is now minus r to r, e to the I, c, x minus c. Okay, and now it makes things a little bit better if you move the 2 pi on the inside as well. Divide this by 2 pi. And as an exercise, you can show that that inner integral, this inner integral, the thing in the brackets, I'm going to put it back in brackets as well. This goes to sine of z minus x over pi z minus x and dz. Okay, well, we just learned in the previous problem here, in the previous video here, that we have this property. So if you look at this property right here, we have this property. So this is going to converge to f of x. Okay, if you look down here we're integrating with respect to x, and it's x minus y in the sine function. Up here, we're integrating with respect to z, and it's z minus x in the sine function, so this turns out to be f of x. Okay, and now this proves, given this, we're doing all sorts, everything that we've done here is completely legal mathematically. I've kind of skipped over why we can change the order of integration here. I explained it's because we're integrating on a compact set on the outside, and the z integral is, the f is absolutely integrable. That's basically the reason. but I didn't like cite any theorems. You'll just look up the Fubini-Tonelli theorem if you want. Anyways, this is what we get. We get this is equal to f of x. So this shows, so this right here is the Fourier inversion formula, and I showed that we recover f of x when you do the Fourier inversion formula. Okay, and so now this gives a way to invert the Fourier transform, which is something that will be important to us because we're going to use Fourier transforms to solve differential equations. Okay, that's it for this video.